Bonjour. So welcome back to QX01, it's Introduction to Quantum Information and its Associated Technologies. So let's have a look at what we've done so far. So last week we covered lecture 1, which was the introduction to the subject. And then we started actually lecture 2 on classical information and computation. And the idea is to see where we start from in order to see where we want to go. And so I will finish that today, and I will then go on to the important notion of the qubit, the quantum bit of information. So that's the program of lecture 2. So we've covered point 1 and 2 already. So I won't go back to point 1 on the history, where we talked about when we went from mechanical computing to the use of vacuum tube and nowadays transistors. And I spent some time telling you a little bit about technologies, about vacuum tubes. Then we moved on to what an actual architecture of a computer looks like. So this one is an old motherboard, but if you look carefully, you will be able to find all these components that we went through with the CPU, memory, input, outputs, and so on and so forth. So we moved on from the fact that we went from hand computation some time ago to what we have these days. And what we then covered is the notion of encoding information on bits, and in particular on some of old technologies now, CDs, DVDs, and so on. And the idea is that any system that has a two-state can be used as a bit of information. So anything that has a head or tail, 1 or a 0, on, off, black and white, anything can be used as a bit of information. And at this particular stage, what we said is that even though if we have n bits of information, we have, in practice, 2 to the power of n states, possibilities. But at the end of the day, when you have n bits of information, you only have n outputs coming from these n bits. And that's the main difference, as we will see today, in fact, compared to quantum information, where we can actually manage to carry on calculation with these 2 to the power of n states. So we went through the so-called Boole algebra in particular, that we can manipulate bits of information. We have various operations using a truth table, so we can have operations of n or not, for instance. So those are called conjunction, disjunction, negation. And as we will see later on, so those operations are basically gates that we use in nowadays computers. And then once we have, so we stopped here last time, so once we have n bits, then we can encode more information. And in particular, what is used, heavily used nowadays, is the so-called Ascii format for the American Standard Code for Information and Interchange. So Ascii format is basically coding into a byte of information. So 1 byte is 1 octet. So 1 octet is 8 bits. So we use the so-called Utf-8 system, which is Unicode transformation format, to go from, so you can see on this table, to go, so you have the ASCII characters. So let's take here, we have letters, capital letters, A, B, C, D, and so on. And then you have the coding in hexadecimal, as well as the coding in binary and decimal. So the binary and decimal. And then the idea is to basically transform each of these characters into a series of strings of zeros and ones, so binary system, in 1 octet, in 1 byte of information, and in basically more than 95% of data transfer from the internet nowadays is based on this system of coding. So for instance, if I want to write my name using the Ascii codes, so these would be the Ascii codes for various letters. You have capital C, that would be 67. So oops, see if I go back here, 67, it's somewhere here, okay? And then so on, so H would be 104, and then R would be 114, and so on, until the last one, which is underscore, which would be 117 for the U. So these would be the numbered ASCII equivalent of these characters, these letters, and then I can translate that into binary numbers made of ones and zeros and basically encode my name in binary characters. And then from then on, of course, I can do much more complicated things and go on to various websites and use various applications and so on and so forth. So it's basically how the internet works in terms of coding. And for that, as I mentioned earlier, we need building blocks. So nowadays we don't use these vacuum tubes. This is real vacuum tubes, the real size of a vacuum tube. So it's the equivalent of 1 transistor, but we use semiconductor transistors, semiconductor technology. So I'm not going to go through the how transistor works in detail because that's not the point here. I'm just to give you the basics. So here is a particular transistor. It's called a bipolar transistor or NPN transistor, and it's made of different semiconductor materials with different doping. So the doping, the N and P are the various doping. So one is an N doping, another one is a P doping for more or less electrons doped into the materials. And so with this, you can make a component, a transistor, which has 3 connectors, so B, C, and E, and they are called C for collector, B for base, and E for emitter. And the idea is, the representation here is that basically through the base, you have a switch button when you can decide for the current to go from the collector to the emitter, controlled by this button, this base button. And this button is simply due to a voltage across the base and the emitter, where you can basically change the state of the transistor, so decide to have a transistor that would let a current through or not, and basically have your 2 states of 1 and 0. So you can see here the typical curve switching on the various, so switching on the transistor and then having the linear zone working of the transistor. So nowadays we use, so these the bipolar transistors were the old technologies. So now we use other type of transistors. Maybe one of the most used one, most famous nowadays is the so-called Mosfet transistor. So Mosfet stands for metal oxide semiconductor field effect transistor. So how does it work? The principle is to basically make use of the capacitance effect that we have in a capacitor using an electric field. So the idea is the following. So again, you have these 3 connector component device, except that now we call them gate, drain, and source. And in this case, is the gate that will be the button to basically let the current flow between the drain and the source. And so how does it work in practice? So again, it's made of semiconductors. So here you have all the different components. So again, I'm not going to go through the detail of it, but just to give you an insight of how it works. So what you have, the idea is that you have a gate, the gate electrode on the top, and then you have another electrode at the bottom. We call it the body electrode. And then you have the drain and the source. And the idea is that when the gate voltage across this area is not on, then there is no conduction possible between the source and the drain, because you have different type of materials in between. And then when you switch on the gate, what you do is you create an electric field that will basically gather at the surface here, that will move the charges and gather electrons at the surface here. Of course, they cannot channel through, because you have this small oxide layer, which is an insulator layer, that's not going to let the current through. So you have a purely capacitance effect, in the sense that you have charges moving up to here, but no current. Okay? No current in that direction, but you do have now in this direction, because after some time you will create here a channel where the charges will accumulate, and now a current flow will be possible between the source and the drain. Okay, so happening really locally under the insulating layer. Okay, so that's the principle of a so-called field effect transistor, because it's based on the electric field effect, and it's a metal oxide semiconductor, because you've got metallic gates, you've got insulating oxide layer, and you have the semiconductor transistor underneath. And just to mention, if you remember in the first lecture, I said that one of the limitations nowadays in the transistors were the fact that we have very thin layers of components, and that in particular insulating layers, and meaning that the current is not supposed to go through these layers because they're insulating. But quantum mechanics tells you that if you have a small enough layer of material, like nanometer scale, then you have the so-called quantum tunneling effect. It means that now, potentially, you can actually have a current flowing through the gate in the body when it's not supposed to be the case. Okay, and that is so. No matter what, this oxide layer getting smaller and smaller. Components are getting smaller and smaller. But at the end of the day, there is an intrinsic limitation where this is supposed to be perfectly insulating. But quantum mechanics tells you that at some point the probability to go through will increase and will be quite important at some point. Right. So when you have these transistors, so there are other issues actually that we can mention. So here you have so there are many types of transistors, basically based on the two that I said, but with various differences for various applications. For instance, if you want to do high power transistors, then you need perhaps different geometry. And also more to the point is you also need different materials. So you can see here all the materials that are used, so semiconductor materials that are used for semiconductors, for transistors. Of course, silicon transistors are the ones that are in most use, but you have other materials like silicon carbide, indium phosphide, and so on. And what I would just want to say here at this stage is that, so you can see here these raw materials, is that there is a material science issue here, in particular to cover aspects of abundance of materials and also pollution, possible pollutions due to some of these materials. Okay, so there is a real issue as well into that, although this is not the topic, but just to be aware that behind there is a lot of material science behind engineering and at some point the computing science. And then when you have this, then you can make many more transistors. You can put them all together. So you have here, so what you start from is you start from what we call a silicon ingot or silicon boule. So I have one piece here. So this is a piece of silicon, and it's basically like a cylinder like this. And what you do is you cut it, you slice it like a sausage. You slice circles out of those, so you make silicon substrate. So this is a small one, but you can have bigger ones like this one. And then from this, you can see perhaps the shiny colors. So those are, so this one is actually an actual lithographically patterned silicon wafer. We talk about wafers, so once we cut them, we have a wafer. And you can see all the different colors are actually due to the different materials that I've deposited on top. So there is oxide, there is metal, and so on. So they will reflect light differently, and that's what you see, these nice colors, okay? So this is patterns. So down here, there are potentially millions of transistors that can then be cut and then used into computers and so on, and phones, and etc. So here you have a typically a chip layout, photolithography mask, sorry. And you can see that the gate layers are in gray, and the source drain layers are the yellow parts. So this is the drawing, this is the drawing out of it. And then this, and what I showed you would be typically what it looks like once the actual lithography with many steps, technological step, engineering step, to photolithography, such a device where you can have various transistors, capacitors, inverter structures, and so on and so forth. Okay. So those are the real building blocks of what we have these days, and the idea is to see how we can have the equivalent building blocks for the quantum transistors, or the quantum part of classical computer. Then, as I mentioned, so you need the next steps is once you have these transistors, you can make gates. So the transistor is 1 bit of information, as 0 and 1. But then once you have this, then you can make much more complicated structures using gates, which can be translated into truth tables. So again, we go back to the Boolean algebra. So here you have some of the gates that the most used gates. So the yes gate is not really a gate; it's just that you have your bit of information. But what you can do is have a NOT gate. So you can take your transistor output and then reverse it. So you can go from 1 to 0 or from 0 to 1. So that would be. So typically, the truth table would be 0 is transformed into 1, and 1 is transformed into 0. Okay? And then you have others, which are 2-bit gates, like the AND gate, the OR, XOR, NAND, NOR, XNOR, and so on. So so the AND gate is basically, so the equivalent of an AND gate is actually a multiplication. So what you do is you take your two bits, so A and B, and then you multiply them together. So let's do this. Okay, so AND gate. So typically, you have your bit A and bit B. So A can take 2 states, so 0, 1. And then B also, so you have, like we said, 2 to the power of 2, so 4 outputs possible. So you have, so we write 0, 1, 0, 1, and then the equivalent will be 0, 0, 1, 1. Okay, and then you make the output, which in this case is the AND gate. And the AND gate, so you have 2 ways of seeing it. So either you take the mathematical expression here, which is the multiplication, so A times B. So if I do A times B, I've got 0 times 0, 0, 1 times 0, 0, 0 times 1, 0, and 1 times 1, 1. So I would have 0, 0, 0, 1 in terms of multiplication. The other way is also by logical operation, where you say that an AND gate is that in order to have an output, A and B both must be of the same state, of the same state 1. So in this case, the only possibility for A and B to be both 1 and therefore to provide 1 is this one. The other 3 are not the case. And then in this case, you have 0, 0, 0, and 1. Okay. By the same token, you have the OR gates. So the OR gate can be seen as a sum, as an addition. So what you do is you go, so in this case, you would, we can write it here, right? So output OR. So again, there are two ways. You can say it's a sum. So if it's a sum, you do 0 plus 0, 0. 1 plus 0, 1. Or 0 plus 1, 1. Or 1 plus 1 would be 2. But in these cases, the is it? In this case, is 1 or 1 would be 1. Okay. So there is no such thing as a 2. But you have at the end the truth table 0, 1, 1, 1. And the other way of seeing it is that the output is 0 whether A or B is 1. Sorry, the output is 1 if the A or B is 1. Okay, so in this case, none of those are 1, so it's 0. This one is 1, this one is 1, and then both are 1. Okay, in this case, you would have 0, 1, 1, 1. Okay. And then you can have XOR, which is in case means, again, logical is to say, well, I want OR, but I want it exclusively. That means I want this one or this one. I cannot have both. So in this case, the XOR would be slightly different, would be 0, 1, 1, 0. And so on and so forth. So I highlighted the three AND, OR, and NOT because actually the primary operations. So what it means is that out of these three, I can construct any others. So for instance, the XOR gate, which can be written like this, so A, B gives C. So in terms of Boolean operation, we can write it C, A, and then the plus with the circle B. And this we can show that actually this one can be written as A plus B times A inverted plus B inverted. And so this one can be actually written as a combination of these three gates, okay? Where you have an AND with the two AND, but with the inverted A and B. You have an OR, and you have an AND again. Okay. So those typically three primary operations will be able to give you the entire family of various gates that you can have. And then once you have gates, then you can make much more complex circuits. So for instance, what you have here on the right-hand side is a 2 4-bit binary adder. So what it means is you take a string of 4 bits, so 2 strings of 4 bits, and then you just add them. You make a sum of them. So like you sum 2 binary numbers to provide the result. And you can see what they will look like in logic. In logic operations, where you have a series of various gates, primary gates, or a bit more complex gates like XOR and 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 so on. And those, so you have these two outputs, the two 4-bit output, and you have the input, sorry, and you have the output result of the adder. And then again, so all of this can be done with transistors. So for instance, here what you see is that if you put, if I go back to the transistors, the kind of transistors we talked about earlier, so if I add 2 transistors in series like this, then what I have basically is it's an AND gate, where in order to have current flowing through these 2 transistors in series, I need to have, so it's an AND gate, I need to have both of them to be on in order to have an output. If one of the 2 is not on, or both are not on, you know, if I did not press the button on any of those, then basically there is no current flowing, and therefore there is no output. Okay, so you need, as they are in series, in order for the current to go through, you need to have both on in order to get the output. So this would be typically, out of 2 transistors, how you make an AND gate. Okay, then you have the equivalent for OR gate, or NOT, or and so on and so forth, and then And then from that, you can make much more complex circuits. So for instance, here you can go to then integrated circuits. So this is perhaps one of the most famous ones. So it's the so-called 7400 IC series. So this was developed by Texas Instruments. So it includes basically four NAND gates. And then this was the first sort of industry standard that used the so-called TTL logic, TTL being transistor logic family, which is basically 0.5 volt type of signal in terms of voltage. Okay. So basically, if I want to summarize, again, so this was a short introduction, but necessary in order to have the full picture on what we stand now and where we want to go to afterwards. So we can go from transistors. So with these many transistors, we can make gates. With these many gates, we can make more complex logic circuits to make operations, additions, multiplications, and so on. We can then integrate all of this into a integrated circuits. We can put all of those components into a motherboard, like this one. This one is fairly old, but you would have the equivalent. All of this will constitute our computers. Now, computers are plugged into networks. Networks are done through fibers. So, for instance, when the technician installed the fiber in my house not so long ago, I recouped that. So this is exactly what you have, and that's exactly how the information goes. So this is on your wall, and this is basically connected to the outside fibers from your providers. In there is an optical signal, and then this output of the optical fiber is then plugged into your box that then get the optical signal and transform it back into an electrical signal into a series of bits, zeros and ones, as we saw earlier, and that what provides directly the signal to the users. Okay. Right. So basically that's all I wanted to say on sort of classical information and computation. And then with this, the idea that we can make extremely complicated systems, very powerful computers, with zeros and ones. And yet, as we saw in the introduction, yet there are some problems that seem to be just impossible to solve using these standard technologies. One of the reasons being the fact that, like I said, so again, if I take this example here, if I have 2 bits, I have 4 outputs possible, 4 outputs. So I have n bits. I have 2 to the power of n outputs possible, and yet outputs possible. But at the end of the day, each bit of information is going to give you one result. It's either a 0 or 1 state. Okay, so at the end of the day, what you do get is only n sort of real output. Okay. So it's a linear system. You have n entries, n inputs, n outputs. And the idea is that if you want to cover problems that require nonlinear time in terms of computation time, and if you remember the first lecture, I showed you the various sort of complexity time dependence. So you have the linear time, which is basically what we would have here. And you have problems that are much more complicated than linear times. And on the other side, where you have sort of problems that can be solved in shorter time. And for that, the idea, as we will see, is perhaps using qubits and using the so-called superposition and entanglement operations. Then we can keep the 2 to the power of n outputs, okay? And therefore have much more, so n entries and yet 2 to the power of n outputs. Okay? So the idea is to see whether quantum can be, can provide superpowers to computers. Right. So now we can start lecture 3. So lecture 3, so we're not going to be able to finish today. We will start today and finish it next week. That's why it's called lecture 3. So 2 are down. And so today, so in lecture 3, so the qubit, these are the 5 aspects I want to cover. So this is, in this aspect, so today we've covered mostly, I'd say, computer science issues. And for this lecture, we will mostly cover a bit of computer science issues, but a lot of math, and also some physics. And in particular, so first of all, we will start by comparing bits and quantum bits. So we've already started, but now we will sort of mathematically explain and write down the differences. Then we will have to talk about mathematical representation, because these qubit, these quantum bits, are particular mathematical objects. So we have to see how to represent them mathematically. So there are rules. So we're just going to apply some rules. We will show a particular representation, which is the so-called block-sphere representation, which is a geometrical representation of a qubit, and it's used quite a lot. And it's also it's very nice, very elegant way of representing a qubit. So we will see that as well. And then at some point, I'm going to give you some physical aspects. So how do we code quantum bit in real life? So as I mentioned in the first lecture, nowadays there are many different systems that are used for qubits. So they are based on superconducting qubits. They are based on trapped ions and other systems. I'm not going to cover all of them, although you will have later on some technological aspects of that. But I'm going to use 2 particular systems as a physical system to illustrate basically how we make a qubit and other aspects. So the first one will be using light, and I will give you the example of a simple qubit, which is to code information on a grain of light, on a particle of light, which we call photon. Okay, and how we do this. So it's not going to be a full course on what's called quantum optics, because this is not the point. But it's for you to understand how in practice we can encode information onto a photon. The second system that I'm going to talk about today will be to use what we call a spin of an electron. An electron has a particular quantum property, like all particles, which is what we call a spin. And this also has 2 states, and this also can be used as a quantum bit. That we will see later on. And then the last part, which seems a bit cryptic right now, is that we will talk about the dual space of a ket. And before that, we would have seen what a ket is. And we will talk about the dual space of a ket is the dual qubit of a ket, and we call it a bra, because the 2 together form a bracket, as we will see. This, for sure, we will not be able to cover today. Right. So, a qubit. So, a qubit stands for quantum bit. So, just some vocab. So, most of notations that you will see for qubit are usually this one, but sometimes you may see it written like this as well. I personally will use a qubit like this, but if you look on the internet or other courses and lectures and so on, some people use this notation. Right, so here we go. You have here, of course, I'll explain a bit more, but you have here what a quantum bit is. And what you can see are several things. The first thing you can see is that there is this kind of weird notation, which use a bracket notation. That's the first thing. The second thing is you can see that as opposed to a bit of information, we have a bit more information here. So quantum bit. So a qubit or a qubit, or also sometimes a qubit. All the same. So if I look at a bit of information, as we said, what we have is a 0 or a 1 as the output. Oh yeah, just remember, so again, this is the French notation system. So the French notation system is that this is a 1. Okay, well, this will never be 7. So a bit of information is 0 or 1. You either get one or the other. But a qubit is both at the same time. So a qubit, we write it like this. So we have this sort of half bracket notation, and this is the Greek letter psi. So we have our two, so we can write it alpha 0 plus beta 1. So first of all, the equivalent of our 1 and 0 are here. So we do have two states. That doesn't change. We still have 0 and 1. So we still have the 0 state and the 1 state. We still need two of them. Except that now we have 0 and 1 at the same time. Okay? So if they are at the same time, I can actually go potentially from fully 0 to fully 1 also. So that means that in a general state, I will have coefficients alpha and beta. So those are coefficients. So I can introduce coefficients, which are coefficients, which is basically the weight I can attribute to each of them. Okay? So in other words, if alpha equals 0, then my qubit is exactly in the 0 state. So that would be the equivalent of that. Okay? Sorry, if beta equals 0. But if alpha equals 0, then my qubit would exactly be in the 1 state. Right? So that would be the equivalent of that. But when alpha and beta are not 0, then I can have the entire linear combination of the two possible. I can go from 0 to 1 continuously. And in fact, as we will see later on, is even more complex than that, because precisely alpha and beta are complex numbers. Okay, so they can take, so alpha and beta are not just real numbers, they are complex numbers. they can be real, of course, but the most general notation is the definition for alpha beta is that they are complex numbers. So another way of seeing it, perhaps more intuitive way of seeing it, is that a classical bit is a switch. You just, put it 1 or 0, depending on the switch. But a qubit is more something of a dial that you can, dial up or down. So you can go dial it up to 0 all the way to 1, and then anything in between. Right? So in a way, it's a sort of analogic way of dealing with the zeros and ones. There is one more information on these coefficients. At this stage is not very important, but just to let you know is that the qubit state, so this object, has to be normalized, whatever that means. But what it means is that there is a relation between alpha and beta, which is that alpha squared plus beta squared is normalized to 1. Okay, and so of course here I put this notation because alpha and beta are complex numbers. Okay, so alpha squared is alpha star, complex conjugate. So there is normalization. And what I wrote here is that I wrote is a normalized vector. So that's the other thing. That's the other way of seeing it, is that even though the notation seems to be weird, it's just a notation at the end of the day. What I'm saying by that is that if I were to, as we will see after, if I were to write this like this, then we would understand it better. Because what we say is, oh yeah, hang on, it's a vector. So it's a vector phi, which is the linear combination of two other vectors, 0 and 1, which can be, for instance, unitary vectors. Okay? And yes, it's the case, in fact. So the qubit here, so mathematically, is a 2D vector. A bit more complex than the ones we see, but that's what it is. Okay? Except that, as we will see, so we use this weird notation, so the so-called bracket notation. Why bracket notation? Because this is what we call a ket. So anything written like this is a ket, but we will see that there is a dual space that we call the with other vectors, although they are not, they're different type of vectors, as we will see, and we write it symmetrically, and we call it bra. Okay, and the reason for that is because, so this is the so-called dual space mathematically. And the reason for that is because we can also combine the two together, as we will see. So we can combine a bra and a ket to form a bracket, hence the name. Okay. So this was actually derived by the physicist Paul Dirac, who came up with this notation, which still seems a bit obscure for now and not make sense, but we will see later on that it does make sense. So, go back to the notion of vectors. So as I said, this qubit here, which is a linear combination of 0 and 1, can be seen as a vector, 2D vector, which is a linear combination of vector 0 and vector 1, which is the equivalent of what we would have in a 2D space, where we have an x and y axis, and we have ex and ey, ex and ey unitary vectors. And you can represent any vector, so in this case the psi vector, in this xy plane. Okay? So that's what it is. So psi will be alpha 0 plus beta 1, or the equivalent that we know since we are small, that is alpha ex plus beta ey, where ex, ey are unitary vectors. I can write it as a vector column. So this would be the notation, so alpha beta. Or I can write it like this as well, saying that is alpha and then 1, 0 for being the ex, or the 0 vector for the unitary vector. And then the 0, 1, so plus beta 0, 1 for the second part. So what we can then define is our ket 0 and our ket 1 by saying that, so now this qubit is alpha 0 plus beta 1, which I can write alpha beta, which I can write alpha, so say I made the choice that the 0 is 1, 0, and this one is 0, 1. Right? And so this would be basically my state 0, and this would be my state 1, which again, in sort of standard Cartesian geometry, would be the equivalent of Ex. So that would be the equivalent of Ex, Ey. So I say equivalent because it's not equal. Okay, as we will see that the space that where qubits live is not the same mathematical space as the one we know in 2D XY Cartesian space. There are similarities, but it's not the same. But it helps to see what a qubit is. So basically, a qubit is just a 2D vector. So this superposition of being both at the same time 0 and 1, well, we know it. It's given by the rotation of a vector going, say, from the x-axis to any angle. So for this, I can use a rotation matrix. So this is the rotation matrix in 2D to move any vector in 2D from one direction to the other. And then I can use algebra for this, where I say, well, if I take my initial qubit state psi and I apply a rotation to it, I will go from, say, this qubit to this one to phi prime now, and I have a different qubit at the end. And it's still a 2D vector. So phi prime would be a 2D vector column like phi, but it's rotated by this matrix. So in general, we can apply any, not any, but some matrix operation. So it would be a 2x2 matrix because it's a 2D vector. So any 2D operation to a qubit to transform it into another qubit. And these matrices, these A's, these A matrices are 2D matrices, which are, as we will see, the equivalent of the gates that we had before, that we saw today, the AND and OR gate. Okay. So all the ingredients are here. So I have my qubit, my general qubit, so in this superposition state. So we will see Now, so this is very mathematical description. And how do we do this in practice? How do we implement this with real systems? So I'll give you the example of light, of how we can encode this kind of qubit onto the polarization state of light. But for now, all we need to know is that we have a 2D vector with alpha, beta, which are parameters, so that happen to be normalized. They are complex. Therefore, if it's a 2D vector, we can apply matrices, 2D matrices, not any kind of matrices. As you can see already, as you can see here, there is a small hat on this matrix A, and that's because it has a significance. I'll tell you afterwards. And we can do any operations, and in particular, any gate applied to a qubit. One more thing, because we're going to be using that afterwards, is the fact that, as you can see here, and we know in 2D standard geometry, we can represent any vector into X and Y representation, but we can also use the so-called polar notation, which is to use the E rho and E theta notation, where rho is the length of the vector and theta is the angle compared to the x-axis. And so we can basically use complex notation to represent that space and transform our alpha beta into rho and theta. The reason why I say that is because it's another way of writing. So now our qubit, so this is our qubit, but we can write it in another way, and as we will see just afterwards, and in particular using rotation, theta, and in 3D we will have to use theta and phi, and that can be represented by this object I called earlier, the block sphere representation. So, okay. So, for instance, here are some examples of matrices that can be used and will be used a lot in quantum information. So in particular, these 4 matrices, and I guess the first matrix is the identity matrix. So the identity matrix just basically leaves alone the qubit. So you apply the identity matrix to your 2D vector, and you end up with the same vector. And then you have 3 others, so we call them Pauli matrices. So for now, we will call them sigma 1, sigma 2, and sigma 3. Again, there is a small hat on top. We will see why. And with these matrices, as we will see, those are actually standard quantum gates, 1 qubit quantum gates that can be used for quantum bits. Okay? And why those are interesting? So these are the Pauli matrices. So you have sigma 1, so 0, 1, and 0. You've got sigma 2, so 0, I minus I, 0. And you've got sigma 3, which are 1, 0, 0, 1. And what you can show mathematically is that in the 2D space where qubits live, so 0, 1 space, these 4 matrices can generate any matrix. So in other words, that's what's written here. So any particular matrix, but any matrix A can be written as the sum or the linear combination of the identity operator, the identity matrix, and the 3 Pauli matrices. So sigma 1, sigma 2, sigma 3. Okay. So it's to show you, so those 4 matrices can generate any 2D matrix. So now let's discuss on the hat business. So the hat business is because the first reason for that is to make sure that these these matrices are not standard matrices. The first reason, which we'll come back to later, is the fact that this A here, this hat here, in physics, means that we make a particular measurement on our system, or a particular transformation. What I'm saying here, and we will see later on as an example, is when we use the polarization state of light, photons, we can manipulate polarization of light, right? We can use polarizers, we can rotate the polarization, we can transform it. And any of these transformation is what we call in quantum mechanics an operator. Okay? And an operator in quantum mechanics is, as we will see, also a matrix. Can be represented mathematically by a matrix. And because we want to give a physical meaning to it, in quantum mechanics, we put a hat on top to say that this is an operator, a physical operator, which means that in practice what you use a device and transform your photons or your electron spin into something else. So that's the first thing. The second thing is that these matrices have to be Hermitian. Okay. Hermitian matrices. So the definition of Hermitian matrices is that the matrix A, so A hat, again this idea, is equal to A and then this cross that we call dagger. Okay, so sometimes it's called cross. I personally prefer the term dagger for obvious reasons. I'll let you think of why. And this dagger doesn't bring much more information because this dagger is actually the combination of two transformations. It's the combination of taking the complex conjugate of the matrix and taking the transpose of the matrix. So dagger, so A cross or A dagger is actually a combination of applying a complex conjugate and then applying a transpose to the matrix. And when you do this, if the result, A dagger, is equal to A, then you have an Hermitian matrix. And so the question you may ask is, okay, and so what? How is that good? Well, it is good because you can show that, as I said, there is a physical meaning to it behind. The physical meaning to it behind is that if you have this property applied to an operator in physics, so again, an operator is actually something that you physically do. So you apply a magnetic field, an electric field, or you polarize light, or you do any of these transformations. Those are physical transformations. That means that they have a physical result. And in order to translate that mathematically, this condition of Hermitian matrices has to be met. So in other words, if you want to give a physical meaning to these mathematical objects, which you do, then that means this mathematical object, you cannot use any matrices or any gates on your qubit. You have to use particular ones which have to have these properties. Property of being Hermitian, and Hermitian means this, or this. Okay, so this is the case for the Pauli matrices. So we can do an example, say with the sigma 2. So with sigma 2, if I take the complex conjugate of sigma 2, I have 0 minus I 0. And then I take the transpose. So the transpose is, the transpose is basically take the symmetrical of your matrix with respect to the diagonal. So that means I will, so in 2D it's very easy, I will just switch that. So if I do this, transpose, I have now 0i minus I 0. Just switch I and minus I. And so this, by definition, is the dagger. So that would be the sigma dagger. And that is precisely what I started with, which is the sigma 2. So this and that is sigma 2. So it is emission. So, okay. Right. So these three Pauli matrices are emission matrices. And the good thing about them is that they can generate any emission matrix A within this 2D space, which is the 2D qubit space. Okay. There are other properties that can link all these matrices, so 1, 2, and 3. So these two properties that we will see later on. But basically what it says here is that from all of these sigma 1, 2, and 3, you can generate, so with two of them, you can generate the third one, and there is a linear combination between them. Right, so, okay. So let's have a look what it does. So I start from my qubit. So I will write it like this notation. So this notation. So now I can apply, so if I apply identity to my qubit psi, I have the identity matrix, and I have alpha beta. So if I look at, so I will generate a new vector. That's going to be psi prime. And this new vector is fairly easy because it's just alpha and beta. So it's just psi. So that's not so interesting, but if I look at sigma 1, apply to psi, then I have 0, 1, 1, 0. Okay? Now I apply it to alpha beta, and I end up with beta first and then alpha second, so I've got beta alpha. So I inverted the two coefficients. So if I write it back to qubit notation, I've got beta 0 plus alpha 1. Or, if I round it in terms of coefficient, I have alpha 1 plus beta 0. Sorry, yes. And what I did here, if I look at the coefficients, so I went from 0 to 1, and then 1 to 0. So I inverted my qubit. Right? So it's an inversion. It's the first gate. It's just an inversion. I can look at the other two. So sigma 2, for instance. So sigma 2. Sigma 2 applied to psi. That would be 0, I minus I 0. Applied to alpha beta. That would give me minus I beta, and then I alpha. Yeah. Right. So in other words, it's I minus beta 0 plus alpha 1. Okay. All right, let's do sigma 3. Sigma 3 would be 1, 0, 0, minus 1 to alpha beta. So that would be alpha and then minus beta. In this case would be alpha 0 minus beta 1. So what I've done here is I just changed the sign here. Okay. So these are the equivalent of the gates, but now for a qubit. So in a way, so in fact, this sigma 1, sigma 2, sigma 3, so there are, for these Pauli matrices, there are different ways of writing them, but we will see later on. So we like to write them, and that makes sense. It will make sense once we look into the block sphere representation. But this one is called the X gate. This one is called the Y gate. And this one is called the Z gate. Okay. And so the way we represent these primary gates, because those are our primary gates now, right? Because if I can generate any gates using any matrices using these three matrices, that means in terms of gate, I can generate any gates using these three Pauli gates now. So X, Y, and Z. So this is how we represent them in a quantum circuit. So this is the first. So the first quantum circuit, the easiest one would be, okay, I have a qubit psi. I apply an X gate, which is the sigma 1 operator, the sigma 1 matrix, which is this one. And I end up with psi prime, which was, as we saw, just to invert the qubit state. So this is the simplest circuit you can think of, where you have an input, output, and a quantum gate in between. So we represent them with like this into a box. For the X gate, sometimes so there are other notations. So this is another notation. So it's a cross with the circle. And so in this case, it's the equivalent of the NOT gate, by the way. And perhaps the least interesting gate, but still exists, is the identity gate, which would simply be a wire, okay? Because a wire, the identity gate does not touch the qubit state. So here we go. So those are the first one qubit quantum gates. So we will see later on when we deal with multiple qubits, and in particular 2 qubits, and in particular the so-called 2 qubit gates, or the control knot. Remember, I talked about it in the first lecture, and I specifically said that this is a very important gate, and we will see why. But this is how we can then generate our one qubit gate using those matrices, which are in physics operators, but mathematically gates, emission matrices generated by this family of Pauli matrices. So if I want to go back to physics, then what does it mean to have 1 and 0 at the same time? Well, I already gave an example of the cat, Schrodinger's cat, if you remember. So if you remember, we said the Schrodinger's cat in a box. There's the entire device where the cat is in a box, and there is a bottle of poison. The bottle of poison can be broken by the hammer, and the hammer can be dropped or not by a switch, and the switch is related to the radioactive decay of an atom. And we said that in quantum physics, a radioactive decay, you can estimate the probability of the atom to decay. So what it means is that after a certain time, what you can say is I can tell you what is the probability of the atom to decay. This probability can be 1%, 2%, 50%, or 100%. Okay? And so Schrödinger's Scat, and that's where the paradox comes from, it says, well, how about, I'm in a sort of 50% chance of the atom decaying or the atom not decaying, 50-50, equal probabilities. Then if I have equal probabilities, Schrödinger's Scat tells you that the switch can be in a superposition state of probability on and off, therefore the hammer to be low or high, therefore the bottle to be broken or not, therefore the cat to be dead and alive at the same time with a probability of 50%. And so we wrote it like this. And this, so with the cat alive and the cat dead, but this notation here is a 50-50 chance for the cat to be dead or alive. And that's the equivalent that we have here, where we said that these two states, so here would be dead or alive, 0 or 1, with a certain weight given by alpha and beta. So as we said, so if I go back to the notation, the first notation where we have alpha, beta, and you remember I said that the state has to be normalized, so that's why I added squared plus beta squared. And we saw that earlier. If beta equals 0, then I'm in a perfectly known state of being 0. If alpha equals 0, then I'm in a known state of being a 1. But if alpha and beta are so squared, have a probability, have a value of 1/2, then that means that my state now would be of equal weight, so 1 square root of 2 and 1 square root of 2. And this 1 square root of 2, when it's squared, is 0.5, so it's 50%. So it's the equivalent of 50% chance for the cat to be dead and 50% chance for the cat to be alive. Okay? So this, with our qubit, is the equivalent of the Schrödinger's Scat paradox. So again, we said at the time, this is a fun so-called thought experiment, but in practice, as I told you, we cannot make Schrödinger's Scat for many, many physical reasons, but we can do that for particles, for photons, for electrons, and for certain properties like spins. So I told you, I gave you the example of quantum tunneling. Quantum tunneling is a good example where if you have a particular thickness of a material barrier, so small enough, you can show quantum mechanically that if you have a particle, so an electron going through it, this electron can be both at the same time on the other side of the material and on this side of the material, or of the wall, on the other side of the wall and on this side of the wall. So it's in a superposition of being in two states, there or here. Okay? So this is not what we're going to use typically for qubit, for physical qubit. We will use other properties like the polarization state of a photon, which can be in two states, so either horizontal polarization or vertical polarization, as we will see. And this can be used as a qubit. This is a physical qubit, and this is also something we can manipulate and make the gates that we saw here. Okay, so we can manipulate the qubit, the photon, through operations and end up with a qubit that has been controlled and changed by a gate. Right? So physically what it means, so a qubit, physically what it means is that this superposition state, so this 0 and 1 state, in fact the meaning behind, in physics at least, is that there is a probability of being in that state or that state. Of course, the most interesting one is the equal probability of being 50% in one and 50% in the other. So typically, so this would be a particular qubit with equal probability of being in 0 or 1. Right. So now let's go to a representation. So this is something, so if you look into qubits, if you look into how to generate them and so on, at some point you will see the so-called block sphere representation. So the block sphere representation is a nice representation because it's very, as I said, very geometrical. So before talking about this, let's have a step back. So in classical mechanics, there are many ways of representing a point in space. Okay? And in particular, there is the so-called spherical coordinate system. So the spherical coordinate system, we have been using it on Earth for a long time, is to represent any point on a sphere through 3, or on Earth, 2 parameters. So 2 rotation. So if we apply this to Earth, if this were to be Earth, then we would have the Earth radius, so that would be the radius of the sphere, and then we would have the latitude and the longitude. In physics, we don't use the latitude, so the latitude would be the angle from the equator plane up to the North Pole. But in physics, in spherical coordinates, in classical mechanics, we use the co-latitude, which goes from the North Pole. Whatever, it's the same idea. The idea is that in classical mechanics, you can represent any space, any point in space by 3 parameters. The so-called radial distance, so that would be the distance from the center of Earth up to a certain distance, so that would be the radius. So on Earth would be the radius of Earth, but it could be anything else to be in space. Then what you do is you need 2 other components, a theta rotation, so that would be this rotation, and this rotation would be compared to the North Pole, so this one. So this is the rotation, so you'd go down. And then you make a projection onto the equator plane, so that would be the equator plane. You project, and then you turn on any point on this plane. And so the combination of the radius, the rotation theta, and the rotation phi basically will allow you to point and to pinpoint any position in space, 3D space. Okay? So you need 3 coordinates, r, theta, and phi, in order to pinpoint. So this is the mathematical equivalent. So you have a basis. So if you want to represent a point M at any space, then you have OM is given by the vector R, and with the so in Cartesian coordinates, so there would be X, Y, and Z. You have, of course, a relation between the R, theta, and phi and the X, Y, Z. So those would be the relations. They are just projections. X would be R sin theta cos phi, and Y would be R sin theta sin phi, and then Z would be just R cos theta. Okay, and so that would be basically R cos theta along here, and then R sin theta, sin theta, and then you have to project along phi, so cos phi and sin phi for the X and Y. So that's a spherical coordinate. And what you can show is that in order to represent a qubit, there is what we call in math an automorphism, so a mapping, if you'd like, between these coordinates and the representation of a 2D vector pointing. So what it means is, so this would be what we call the block sphere representation. And to the block sphere representation, so likewise here, you have a North Pole and a South Pole. And the North Pole would be, so say we can decide that this is the 0 state, and the South Pole is the 1 state. So if you point North Pole, your qubit is just in that state. And if you point in the South Pole, your qubit in that state. And in a general state, what you would be, so, and if you are on the equator plane, you also have particular, so the equator would be in xy. Those would be a particular, so a particular direction, so along x and y. So along x, so along x you would have where this state, so 1 square root of 2, 0 plus 1, that's the one we used here. And then along, so that would be along x. Along minus x, you would have the same thing, but pointing the other way, so 0 minus 1. And then for y, you would have the equivalent, but this time in sort of complex plane, you would have the 1, 0 plus I1 and 0 minus I1. And then any point, then of course, so these are 4 particular points, or 6 particular points, so north, south, y, y minus y, x minus x, or x equivalent. But of course, you can point at any space, any point in space in this sphere. And in this case, you can show, so this would they'll be more expanded into the tutorial, that this qubit state can be written like this, where you have cosine of theta over 2 plus sine of theta over 2 and then exponential I phi. And so this is the exact equivalent of those, alpha, beta, but in that respect of block sphere representation. One thing I didn't say is that in the block sphere representation, we have theta and phi, and we don't have r in the sense that r is the norm of the vector, and the norm of the vector, as we said, is 1. So it's a sphere that has a radius of 1 because it's normalized vectors. So now I can represent any qubit. So for instance, if I want to look at this particular qubit, Q, let's have a look. So this representation, Q, so say I want 1 square root of 2, 0 plus I1. So that would be 1 square root of 2, 1I in vector column notation. And in order to get this, what I have is, so R equals 1, because it's a normalized, this is a normalized vector, so it's 1. The R will always be 1 in this block sphere representation. And then theta would be pi over 2, and then phi would be pi over 2. Because if I take that representation of a qubit, so Q, in this case, can be written as cos theta over 2, 0, plus sine theta over 2, then exponential I phi, and then 1. So if I have theta equals pi over 2 and phi equals pi over 2, then I have cos theta, pi over 4, 0, plus sine pi over 4 exponential I pi over 2, 1. So pi over 2 is 45 degrees, and 45 degrees is square root of 2 divided by 2, or 1 over square root of 2. So this is 1 over square root of 2, 0, plus also 1 over square root of 2, times exponential I pi over 2, exponential I pi over 2. If I take cos pi over 2 is 0, plus I sine pi over 2 is 1 times I, so I've got I, 1. Okay? And so at the end, I have 1 square root of 2, 1 I. Okay? And I can generate any others. So for instance, the other one. So same idea. So oops, I can't. So same idea now. If I have this qubit, which is 1 square root of 2, 1, 1, then it's R equals 1, theta equals pi over 2, and phi equals 0, because, well, we have the same thing, so cos pi over 4, 0, plus sine pi over 4, exponential 0, and 1. This is this is 1 over square root of 2, 1 over square root of 2, 1. So I've got 0 plus 1. Okay? And so on and so forth. Right. So this is something that is used quite a lot, the block sphere representation. And it's a nice way, in particular when you want to apply a series of gates, because these Pauli matrices, these gates, these X, Y, and Z gates, one qubit gate is basically a rotation, is applying a rotation of the qubit into a specific direction, so project it on the North Pole, or project it on the South Pole, and on the other side, and so on and so forth. So it's basically, I mean, the Pauli matrices are the rotation matrices that we showed earlier. It's exactly the same thing. The standard rotation matrices, they are in a way also similar to the, I mean, can be also generated through the Pauli matrices. And there is a direct mapping between these so-called classical spherical coordinates and the block sphere. In this case, what we talk about now is a state vector. So the state vector psi, the qubit, and the block sphere coordinates, which I'm going to be given by theta and phi. Okay, so those. So in fact, like I said, this is never used because it's always normalized vectors. So these two are enough to quantify your qubit in the block sphere. Right. So now let's have a step back. As promised, let's have a look at how we do this in practice. Okay, because so how do we have in practice a superposition state? How can we be both 0 and 1? Of course, so Schrodinger's Scat, we already covered that this is not possible, and even if it were to be possible, it doesn't seem like a good way of producing a qubit. So but with light, we can. So I'm not going to, again, this is not a course on physics, so I'm just going to give you, so for those who know, then they know, it's very good. For those who don't, then if they're more interested, they can have a look. But supposedly they've seen a minimum of electromagnetism at some point. So that's all I'm asking. And if not, then just, keep up and follow. So the idea is what? Is that, so it's basically a crash course in 2 or 3 slides on electromagnetism, that's all. And the idea is that, so light, is an electromagnetic wave, okay? And what is nice about it is that there are equations called Maxwell's equations that basically define electromagnetism and therefore define light. Those are the Maxwell's equations, so they can be quite complex, and they can in particular give quite complex results. But we will use them, or we actually won't use them, but if we were to use them, we would use them only in a very simple hypothesis that can make it easy to handle. And so what is an electromagnetic wave? Well, you have a nice representation here of an electromagnetic wave. So an electromagnetic wave is a propagating wave. So in this case, it propagates through the z vector, to the z-axis, sorry. So first of all, we can define what we call a wave vector. So it's a propagation vector, so we call it k. And k has units. K is 2 pi over lambda. And lambda is the typical wavelength. You can see here the typical wavelength of the electromagnetic wave. And so what is an electromagnetic wave? As you can see here, an electromagnetic wave is simply a propagation wave that is a constant balance between the oscillation of the electric field and the oscillation of the magnetic field. So there's a constant balance between the two. And that constant balance allows basically electromagnetic waves to propagate in space. Okay? So you can see here, so typically if you have propagation along the z-axis, you have oscillation of the electric field. So in this case here is oscillating along the x-axis. And you have oscillation along the y-axis for the magnetic field. And both of them oscillates in a balanced way. So at this stage, we can make, as I said, a simple hypothesis, and we will assume that these waves can be seen as simple plane waves. Okay, I'll give you the explanation. What it looks like afterwards. And these plane waves are actually so the easiest solution of this equation. And this equation is the so-called propagation equation of light, or also called the D'Alembert equation, but whatever. The D'Alembert equation is a more general equation than we'd find in wave physics in general, or in wave systems in general. We have this kind of equation. And where does this equation come from? This equation comes from basically the resolution, the solving of Maxwell's equation in particular cases. And in this case, is the solving of Maxwell's equation in vacuum, so in space. So here, for instance, light that is going into this room can be seen as a propagation of light in vacuum. Okay? So propagation of light in vacuum means that there is no charges rho, there is no density of current J. So there are simplification in this equation, and then basically if you take these 4 equations and just shake them, at some point you can show easily that you end up with this propagation equation. And that's nice because this propagation equation is what exactly generate and explain the propagation of light in space. Okay? And as you know, or you may have heard of, light is actually polarized. So what does it mean? There's a very physical sense for that, and how we define it. So first of all, let's go back to what we said. We assume that the electromagnetic wave is a plane wave. So plane wave means that the electric field is going to be, so this oscillating field here of E is simply going to be defined as an amplitude times cosine of kz minus omega t. K is the propagation vector. Oops, sorry, it's here actually. K is the propagation vector. Z is because it's propagating, in this particular case, along Z. T is the time. And omega is the frequency of the wave. So omega, the frequency, is directly related to the wavelength lambda. Well, inversely related, because lambda equals c times t. C is the speed of light in vacuum. T is the period of oscillation, which I can rewrite c equals 2 pi over omega. Okay? And this is the wavelength. So one thing you need to know is that in electromagnetism, in order to define an electromagnetic wave, you don't actually need to know the electric field and the magnetic field. Only the electric field component is enough, because they are, well, you can see, you can deduce the magnetic field. You see here, for instance, you can deduce the magnetic field from the electric field. So the good thing is that you don't need, so in order to define that wave here, all I need to know is this. I can find B from that, and I don't need that. It's a redundant information, first of all. Second of all is, as I said, light is polarized. So what does that mean? And in particular here is that, as you can see here, the electric field is oscillating along X. So it's oscillating like this and going towards you. But I could have chosen the electric field E to be oscillating along Y. It would have been the same thing. And then B would have been along X. And so the way to introduce the polarization states, already I'm talking about states, two states, is that light is polarized according to the direction of the electric field. That means basically if I have an oscillation along X or an oscillation along Y, then these would be two polarized lights, one along X and one along Y. And the polarization state, for instance, this is how you can get some nice colors out of this. So this is basically, you would press some plastic, and then the stress on the plastic would change the refractive index, whatever. But the fact is that if you look into that with specific polarized optics, and you will see these nice colors, because there's also a dependence on the wavelength with the refractive index and the polarization state. This is a polarization effect. I talked about color. We can see color. Well, in light, the color of the light is simply the wavelength. Okay, so if you have short wavelength, for instance, 400 nanometers wavelength, then you have UV color, and if you go towards 700 nanometers, you have red color. But whatever, the fact is, basically the wavelength of your wave is the color of the light. And what the message to take home here is that these two states, so E can oscillate like this, but it could also oscillate along Y, are two possible directions, one along X that we can call vertical, and one along Y that we can call horizontal. And those will be the two states that can be used to actually encode information on 204. So how do we do this? Well, if I look at the linear polarization along X or Y, then this what it will look like. So I have a plane wave, so it's simply oscillation, so moving towards you and in time, along X and along Y. But the thing is, this is along these two axes, but I could also use some optics and then turn, so to go from here to there, but I could also turn it to halfway through, to in between. That would be sort of vertical, horizontal, and then diagonal, or anti-diagonal, And those, well, it's easy. Those are vectors. So if I want to know what the diagonal state would look like, well, it's simply the sum of x and y. And the anti-diagonal would be Ex minus Ey. I can have more complex states. I can use, I can have circular polarization. So in this case, what you have, so that means that you have a phase in between these two. Huh? So you would have a phase between the x component and the y component. So that's where the phase comes from, this pi over 2 here. That's the phase. So that means that now you would oscillate, but you would also turn and go like this. So you can either do circular right, or you can do circular left. So you have two possible circular polarization states. But if I take a step back, here, the fact that I have Ex plus Ey is the equivalent of this vector we talked about earlier, right? So it means that if I use light, and in particular a quantum particle of light, which is a single photon, and if I look at the polarization state of a single photon, then of course here we're talking about classical optical waves, but properties will follow exactly the same way with photons. So what it means that I can put a single photon, a single particle, so a single object, into a diagonal polarization. But a diagonal polarization, you can see it here, would exactly be the equivalent of that. In fact, so here, so for diagonal polarization, also usually use British English notations, but as you can see here, sometimes there is the American English notation, but it's the same thing. And so E in the diagonal state is written E0 cos cos kz minus omega t Ex plus Ey, right? So I can rewrite this as being E0 cos kz minus omega t Ex plus E0 cos kz minus omega t Ey. And by analogy, this could be my qubit state 0. And this could be my qubit state 1. And in fact, there is a direct transposition to be done. And these are the same. This is the same. So I can be, in fact, it's the same weight in terms of amplitude. And this could be the equivalent of the 1 square root of 2 and the 1 square root of 2. So I would have here 1 square root of 2, 0, plus 1. So this is typically how we would use a physical system, in this case photons, so polarized light, to encode information. So I can decide now to say, well, the oscillation along X polarization is my 0 state. The polarization along Y is my 1 state. Then if I transpose the diagonal, anti-diagonal, I've got 1 square root of 2, or the equivalent 1 square root of 2, 0 plus 1, or anti-diagonal would be 0 minus 1, with the 1 square root of 2. In circular polarization, I have this phase, but then this phase term, in complex notation, would simply be the addition of an I, or I over 2, or minus I, and so on. So using, you remember the notation, using the complex notation with theta and phi, where we, in fact, it's still here. Here we go. using this notation, I can show that the equivalent of this right circular polarization and left circular polarization is going to be a state like this, which is 1 square root of 2, 0, plus minus I over square root of 2, 1. Okay? And as I can control, so I have optical elements that can control the polarization state as I wish, then I can basically generate any state like this, therefore any qubit like this, using the polarization state of light. The only condition for that to work is it has to be a quantum system, therefore it has to be at the single photon level. And that, of course, technologically is not easy to do, but this is done nowadays. We can do that. So we can generate single photons. That's the hardest part, actually, because once we do, then it's easy to manipulate the polarization state of this photon. So to manipulate this qubit using optical elements, we can do that, and therefore generate various gates and do single qubit gates on our photon qubit. Just to finish, there are so people who use photons like I do, sometimes they use the vertical horizontal notation, so you would see a V and an H, but that's the equivalent of 0 or 1. It's just that the vertical or H, vertical horizontal polarization. Right, so I think I'll stop here for today, and so next week I will finish off the lecture 3 on qubit, and I will start with multiple qubits on lecture 4. Thank you.